Hello everyone, I'm Jiahui from Tsinghua University. It is a great honor to be here to talk about our work on capacitive angle sensors. Many application scenarios, such in industrial robots and gimbals, require angular displacement sensors from low accuracy to high accuracy. In consumer electronics, micro-air vehicle, and other fields, there are stricter requirements for size, weight, power, and cost of angular displacement sensors. Capacitive angle encoders have advantages such as simple structure, high precision measurement, and miniaturization potentials compared with other angular measurement sensors. In formal literature about the capacitive angle sensors, the sensitive structure was fabricated by PCB technology, while the demodulation circuit was utilizing discrete components or FPGA chips. The development of applying MEMS technology to capacitive angle encoder sensitive structure fabrication instead of PCB technology leads to better temperature characteristics and higher fabrication accuracy in limited size. However, the size of interface circuits limits the miniaturization of encoders. Some capacitive angle encoders utilize discrete components to demodulate signals and obtain angle information, which causes waste of circuit footprint and difficulties of integration. Compared with FPGA chips, ASIC costs less volume and less power to achieve the same sensor sensitivity. So, for further size reduction of angle encoder, integration of a MEMS fabricated sensitivity structure and an ASIC can be an economical alternative. The sensitive structure of the capacitive angular displacement sensor consists of a rotor and a stator. The stator includes an excitation electrode and 4 sides of collecting electrodes. The rotor includes a coupling electrode and sensitive electrodes. The mathematical schematic of the sensitive structure is depicted in the first figure. In measurement progress, an excitation signal acts on the excitation electrode of the stator. Then a voltage signal having the same frequency is obtained on the coupling electrode of the rotor. As the sensitive electrode is connected to the coupling electrode, the voltage signal is feedback coupled to the collecting electrode. The relationship between the 4 sides of the collecting capacitance and the rotation angle can be expressed by the following formula. Therefore, the angle information is decoded into the orthogonal signals. To fabricate the sensitive structure of the angle encoder, MEMS technology is used. The stator consists of a glass substrate, interconnection layer, insulating layer, and sensitive layer. First, metal layers are spattered on the glass substrate, where the titanium layer works as an adhesive layer. Photolithography and wet etching are utilized to pattern the metal layers to form the interconnection layer to extract the signal of the sensitive layer. Then, silicon oxide is grown as the insulating layer, and the holes of interconnect vias were formed by photolithography and wet etching. Finally, aluminum metal is spattered by physical vapor deposition and patterned by photolithography and etching to form the electrodes on the sensitive layer. The sensitive structure is mounted to an ASIC. It is integrated with an ASIC which enables angle calculation and compensation. The ASIC is designed in an analog-digital hybrid architecture to achieve low power consumption as well as a small footprint consisting of a charge-to-voltage converter with capacitance cancellation array and signal delta modulation with a 3-bit quantizer and Cortex-M3 digital cornel. To ensure that the scale factor of the capacitor voltage ratio is maximized at low voltage, the DC capacitor cancellation array is used to cancel the DC component in the detection capacitor. Then a CV converter is used to convert the detection capacitance signal into a proportional voltage signal. In the formula shown here, we can see how the DC component of the detection capacitor is cancelled, and then the charge of the capacitor is transferred into voltage signal by the CV converter. As is depicted in this picture, an SDM module is connected to the CV converter and is used to convert the analog signal to a digital one. The SDM module includes a resonator, a quantizer, and a 3-bit DAC feedback network. The resonator is used for bandpass sigma delta modulation of the voltage signal output by the CV converter. It provides a third-order noise shaping ability. The quantizer is used to convert the signal output from the resonator into a base stream signal. A switch capacitor DAC is implemented to form a negative feedback analog signal. The bandpass SDM module is able to transfer the quantization noise introduced by the quantizer out of the baseband, and therefore improve the signal-to-noise and distortion ratio of the modulator. The readout circuit is implemented in a standard 1.18 micro CMOS process with a chip area of 77.4 square millimeters and mounted on the PCB through chip onboard packaging. The stator of the sensitive structure is contacted with a readout circuit via gold wire bonding and fixed on the 3-degree of freedom displacement platform. The rotor is fixed on the turntable to test the characteristics. To determine the resolution characteristic of the encoder, a step test with 0.02 of a degree increment as well as 2.5 seconds time delay is performed. The corresponding output is shown in the first figure, suggesting that the resolution of the proposed encoder is considered better than 0.02 of a degree. The dynamic characteristic is also verified. Adjusted to oscillation mode, the turntable can oscillate in a side angular frequency. The measurement accuracies under varied oscillation frequencies are calculated by the ratio of the encoder angle signal to the reference output of the turntable as shown in the second figure. Further, to analyze the dynamic arrow in the linearity test, the turntable rotates 360 degrees continuously. The output is recorded and compared with the turntable position to obtain linearity arrow. As depicted in the third figure, after composition, the linearity arrow is below 0.12 of a degree. In this paper, we proposed an ASIC for a capacitive angle encoder. The performance comparison of the proposed angle encoder and previous encoders is summarized in this table. As noted, test results show that the stability of the encoder is up to 0.001 of a degree, and the accuracy is 1/100th of the degree, and the power consumption is less than 200 milliwatt. However, this encoder already has the advantages of low supply voltage, low power consumption, and small volume compared with previous encoders, which makes it can be widely applied to portable electronics such as robot arms, customers' gimbals, and arrowheads. The proposed encoder has a wide application range. Based on the results listed in the formal table, the advantages of the proposed angular sensor could be listed as follows. The first is the ASIC MEMS integration system. The proposed sensor relies for the first time on ASIC MEMS integrated angle sensor measurement system. The sensitive structure of the sensor fabricated by MEMS technology can maintain high precision while the area is very small. The ASIC also can achieve higher performance and power efficiency with a smaller volume. As the result, an ASIC MEMS integration system is suitable for high precision application requirements. The second is the competitive dynamic performance. Some application scenarios of angle sensors such as unmanned aerial vehicles and aerial gimbals have high requirements for dynamic characteristics. The previous angle sensor has less description of the dynamic characteristics, while the proposed sensor can detect the angle accurately, even under the oscillation condition of 120 Hz. The last but not the least is the low slope NC, which is small size, lightweight, low power consumption, and low cost. The diameter of the proposed encoder is limited to 30 millimeters, which is considered competitive for angular sensors. That's all. Thank you. Thanks for your listening.